Hello, class. Welcome back to Physical Science. I am Mr. Shrum. I hope you all had a great break, and I hope you are ready to get back into physical science. So, if you remember before break, we talked about Newton's three laws of motion. We talked about the first one, the law of inertia. That law dealt with objects and how they wanted to continue doing what they were originally doing. So, for instance, if an object was standing still, that object wants to stay standing still. Or if an object is moving in a straight line at a constant speed, that object wants to continue moving at a constant speed in a straight line. And the easiest real world example would be a car, right? So if you are moving in a car and you come to a stop, you feel a force forward. You lurch forward as the car stops. And you are feeling inertia. That car and you want to continue moving forward, but the brakes have exerted a force in the opposite direction, bringing you to a stop. And then when you push your foot on the gas again and you move forward, you feel your body being forced backward. And that is the inertia from you and the car wanting to stay still. But the gas, you are engaging the engine and pushing the car forward. So that force, when you stop a car or when you make a car go forward, that is inertia. The second law, we dealt with F equals ma. And that was just applying that equation to a bunch of mathematical equations. And the third law is much like that second law and broken down to its very easiest components. For every action, there is an equal and opposite reaction. So for every action, you have a reaction going the opposite way, okay? If I push this pen across the table, right, there's an equal and opposite force going the other way from friction. And we'll talk about that later. Or if you have a plant sitting on a tabletop, there is the force due to gravity pushing down, right? Gravity is pulling that plant downward. But there is an equal and opposite force keeping it in place. And that is called the normal force. Sometimes that is called the support force. But think of balance. The third law is all about balance and how to achieve that balance. This first situation is called static equilibrium. If we have two objects exerting forces on each other, but the net force is equal to 0, they're in static equilibrium. So this opposite and equal action reaction means that they're standing still in static equilibrium. Now, if we wanted to move this object or move one object instead of the other, in the real world, we deal with friction. That is a contact force. Contact meaning it has to make contact with an object to exert force on it. and it opposes any motion. And that means if you wanted to move something this way, a friction force is opposing it in the opposite direction, right? So think equal and opposite. That's all the third law really is. And then we just apply that idea to various situations, and we try to describe it in a mathematical way. And to do that, there are two equations for friction. There is static friction. Static friction is the amount of friction force there is to move an object. So if there is this plant on a table, this equation calculates how much force you would have to use to make it move at all, okay? And that is the force due to friction equals a coefficient of static friction. This coefficient depends on the material, the type of material you're moving on. So rougher materials like cement or concrete, those will have a higher coefficient of friction and therefore more friction overall. But if you're on a smooth surface like ice, you see how ice skaters glide, there's not a lot of friction going on. So this coefficient will be lower in smoother surfaces. So we have the force due to friction is equal to the coefficient of static friction times the normal force. And that is just the support force up here. Okay? And in these problems, you're going to be given two numbers and you'll need to find the third. So you may be given the coefficient and the normal force, and then you need to calculate the force due to friction. Or you're given the force due to friction and the normal force, and then you'll have to find the coefficient. So that's all you're going to be doing with these mastery test questions. There's static friction and then kinetic friction. Static friction is the force you need to make it move at all. And then kinetic friction calculates the force once the object is moving. So static friction, let's say this pen is laying still. I need to exert a certain amount of static friction to make it budge. And then once it's moving, you can calculate the amount of friction it's experiencing when it's moving as well. So static to make it move, and then kinetic friction calculates it when it's actually moving. It's important to remember the difference, but in the equation itself, it'll kind of tell you which way to go. And if you are having trouble with any of these questions, my advice is to draw it out. If in doubt, draw it out. And in physics or science, typically physics, we have FBDs, and that's called free body diagrams. Free body diagrams. But I'm a visual learner, so if I don't understand something, I'm just going to draw it out, right? So you'll have an object. It can be just a dot or a box, whatever you want. There will be a force due to gravity pulling it downward. There's an opposite reaction, the normal force in the upward direction. And then if you apply a force this way, F applied, there is an opposite force due to friction. So if you're trying to move an object this way, there's a friction force opposing your applied force this way, okay? And once again, the steps will be find normal force and then find friction force. Or it may flip. You need to find the friction force first and then find the normal force. But you will be given all of the information you need. Just take your time, think about what it's asking for, and then solve your problems. So let's take a look at some of these questions first. All right, so we kick a ball with a force of 26.3 newtons. Let's draw it out. There's you, I guess, and there's a ball. Bam. Here, let's see. Yeah, now you can tell it's a ball and not another stick figure head. So you, bam, you're like all strong and you kick it with 26.3 newtons this way. But it's asking what is the magnitude and direction of the force you experience? So remember the third law. Newton's third law. Equal and opposite reaction. So if you kick it this way, 26.3 newtons, the ball also exerts a force on you in the opposite direction, right? Remember, equal and opposite reaction. That's a big part of this. All right, you think you got that? Let's move on to the second question. So here is our first example of a static friction question. Given that 16 newtons is enough force to move an object, and the coefficient of static friction equals 0.380, what is the normal force, F of n? So you're given the force due to friction. Whenever it says is enough force to move an object, that's a red flag for friction force is 16 newtons. And then they give you the coefficient. So all you need to do is plug these numbers into the equation and solve for the normal force, right? Plug and chug. And then divide 16 by 0.380. And I'll let you do that on your own. But yeah, pretty straightforward question there. And then here's another conceptual question. Imagine there's a tug of war event. Team A, I guess there could be more people on a team, right? That makes more sense. So team A and team B, they're all tugging on the rope. And you're told team A pulls with a force 103 newtons. So they're pulling that way, bam. 103 newtons. But the rope does not move in any direction, okay? If the net force is 0, then what does that mean, right? So if they're pulling 103 newtons this way, but nothing happens, that means there's an equal and opposite 103 newtons being pulled by team B. If nothing's happening, if it's in equilibrium, the sum of all forces equals 0. Net force is equal to 0. Equal and opposite forces. All right. So I may start to sound like a broken record, but this is to make sure you understand. This will come up in the unit tests, but just be familiar with these types of questions. They'll all have this similar format. So in this one, you're given the normal force and the coefficient, and you need to know the minimum applied force to move the object. So you may be thinking, well, Mr. Shrum, that sounds a little different than before. Well, actually, it's the same setup. All this means is you have to at least use a force greater than or equal to, that's what the sign means, greater than or equal to the friction force due to static friction. So you're just using this equation again, and you find that number. So you see what I mean when you need to slow down and say, well, what is it really asking me? Yeah, you're just using the equation. So don't let that scare you. All right, so that was a static friction question. And now we have a kinetic friction question. And the only difference is the object is already moving and you need to find the coefficient, right? So we're using a different equation. You're using a different coefficient, but you're given all the information you need. So I draw it out, always draw it out. So we have our little free body diagram. We're told Anna is pushing a book on a table. So there's a book. She is pushing the book this way with 19.5 newtons. We're also told the normal force is equal to 51.7 newtons. So I put that there, normal force. What is the coefficient of kinetic friction? So this is the equation. We're given 19.5. That has to equal 19.5 has to equal the force due to friction. You're given the normal force, so all you do is solve for the coefficient. Okay? Not too different from the static friction question. It's just because this object is already moving, this is the friction it's experiencing while moving. Okay? And another conceptual question, 6 and 7 questions actually. But to move an object, the force applied has to be greater than or equal to the force of static friction. Otherwise, it won't move, right? And if the sum of forces equals 0, if the sum of forces in an action-reaction pair are equal to each other, this always equals 0, okay? Because there's always an equal and opposite reaction. Bop, bop. Okay? You need to apply a certain amount of force to make something move, and then you have to apply a certain amount of force to keep it moving. And there are equal and opposite reactions of forces in Newtonian physics. Things get a little more complicated later, but right now, this is all you need to focus on. And then our last kinetic friction question. You're given the coefficient, you're given the friction, the force due to kinetic friction already. And all you have to do is solve for the normal force. So a very similar setup to before, but key tip here, remember scientific notation. Some of the answers on the multiple choice questions are given in the scientific notation. So remember, for example, this is not the answer, but if you calculated 120 newtons in the Edmentum answers, they may put that in this format, 1.2 times 10 to the second power. That is the same thing, okay? So keep that in mind. If you don't see the answer, it may be in this format. And then one of the last problems, this is a little different than before here. So this concept is a little different, but it's essentially the same thing. But tension is another contact force. So it has to be in contact with an object, and it pulls on objects at the ends of the strings, ropes, cables, or cords. And there's a tension force on the objects. So I drew this out. Here's a table, and attached to it is a pulley, kind of like a wheel. And you can attach a string or a cord over this pulley. And then on either end of the string, there is an object. And the tension force pulls away from the objects attached to the string. So that there's a tension force pulling away from this mass attached here. And then there's another force due to tension pulling away from the object here. Okay? And here's a more simple problem. There is a bird feeder tied to a cord. The cord is attached to a tree branch. And you're asked to describe the tension force. So here's my little tree branch. There's a little bird feeder. But it's attached at the ends to a branch and this bird feeder. So the tension force pulls away from the objects attached at the ends. So it'll be kind of pulling towards the center of the string. So there's a tension force pulling down on the tree branch, and then there's a tension force pulling up on that bird feeder. And the arrows point in the correct directions. Tension always pulls on the objects attached to the ends. So it doesn't make sense for tension to like push against the object, right? That's not how it works. The bird feeder is pulling down due to gravity, and there's that tension force pulling up in the opposite direction. right? This cord is pulling down on the tree, the force due to tension. And then there's another force the tree branch has to exert to keep the branch in place, okay? So think opposite and equal reactions here, right? That's tension. It's a little different than what we looked at before, but I think you guys can understand that. And if you do need more help, send me a message in Canvas and I can show you more examples of tension. But think of tension as pulling on objects that it's attached to. And then our last problem today is the chair with wheels. This is another conceptual question to check if you understand what would happen in the real world. So picture Tom on a chair with wheels and then Ted on a chair with wheels too. And if Tom pushes Ted that way, he's gonna move too. So if Tom pushes Ted this way, Tom pushes Ted that way, Tom is on wheels and he also moves. And he's gonna move away from Ted because he's pushing a force this way. There's an equal and opposite force going the other way. So this is what they're gonna look like afterwards. They're being pushed away because of, that's right, Newton's third law of motion. Okay. Are we having fun yet? Do you understand the third law of motion yet? Are we good? Hopefully that gave you a better understanding of the last of Newton's laws of motion. For every action, there is an equal and opposite reaction. That ties together with the law of inertia, and the force is equal to the mass times acceleration. It all ties together and explains most of the way the real world works in physics. Yes, just to go over equal and opposite, can't say that enough, equal and opposite reaction. It'll come up again and again. Static equilibrium, remember friction opposes motion. If you want to go this way, friction will want you to go that way. Tension pulls on objects it's attached to. And if in doubt, draw it out. Have some fun. You can draw things, sketch things out. As long as you're familiar with the way forces are applied, this is great practice. If you move on to physics or higher level sciences, like in college or technical colleges, there is a lot of this going on. But it is problem solving. So draw a picture, get your bearings, and yeah, you guys can do this. And if you need any more help, message me in Canvas, and I will do my very best to help you on your physical science journey. But thank you, and I will talk to you guys next time. All right. Have a great day.